today we're going to be learning about derivatives of elementary functions. So don't let the word elementary, confuse you, right? So for this, elementary just means, regular functions like like natural log of x, the regular log of x, the exponential of x, maybe some trigs. Elementary is just like basic functions, right? So let's start with the easiest one, I think, in my opinion, e to the x. So this is the function that you'll see over and over and over again in math, right? So if we want to take the derivative of e to the x, it'll probably be the easiest one for everyone to remember. It's just going to be e to the x, right? And if you take the derivative of e to the x, it's just e to the x. And again, you take the derivative of that, e to the x. So no matter how many derivatives you take, it's always going to be e to the x, all right? But things change when you have, let's say, the derivative of ex squared, right? So here we're actually going to be using the chain rule, right? The reason is because we have, well, let's walk through this example first. When we take the derivative of e to the x, we get e to the x, right? So just assume this x squared is just x, right? So we're going to rewrite it again, e to the x squared. Then you have to take the derivative of the inside, right? That's what the chain rule is. Take the derivative of the outside and then the derivative of the inside, right? So the reason why we're using the chain rule is because this thing right here could just be assumed to be some variable y, right? Some variable y, and then it's e to the power of y, and e to the power of y is e to the power of y. But now we have to take the derivative of the inside because that y is x squared, and x squared isn't just some linear function, it's something of higher order, so it's ex squared. So just like the chain rule says, take the derivative of the outside. The outside would be itself, and then we take the derivative of the inside. The derivative of the inside is just 2x, right? And inside is defined as inside the parentheses. That's what the derivative of the inside means. The derivative of the inside of the two parentheses, right? So the derivative of x squared, that's 2x, right? So if I say what's the derivative of this, it would be 2x e to the x squared, right? So I think we can do probably one more. Let's say we're taking the derivative of e to the, in this case, 2x, right? It's still an application of the chain rule. So assume that this 2x is a y. So it's, what's the derivative of e to the y? Well, e to the y. But in this case, we're going to write y again in terms of x. So it'd be 2x, right? And then the derivative of the inside. The derivative of 2x is just 2, right? So 2e to the 2x is the derivative of this, right? So now we're going to move on to, let's go with another common one. Let's go to natural log of x. Alright, so let's say we have the natural log of x and we want to take the derivative of this. Well, the derivative for natural log of x is always going to be 1 over x. Alright, but things change yet again when the inside part is no longer just an x. So for example, if I have natural log of x squared, it would be 1, the derivative would be 1 over what's inside, but then it's the chain rule again because we have an inside of the parentheses that's no longer linear, right? If it's not an x, then we have to use the chain rule. If it's something more than just an x, then we have to use the chain rule. So here we have something more than just an x. We have an x squared, so we have to take the derivative of the outside. Well, what's the derivative of x squared, of the inside, I mean? What's the derivative of x squared? Well, it's 2x, right? So all this times 2x. So if it's times 2x, I can just write it in the numerator. 2x over x squared, right? And then the x's can cancel out, right? And I'm just left with 2 over x, right? This is just a case of simplifying, but the real answer would be 2x over x squared. But let's do one more. So let's say I had natural log of negative 3x, right? Well, if you want to take the derivative, it's 1 over what the inside is, and then we take the derivative of the inside, because it's the derivative of the outside. The derivative of natural log will give us 1 over something, and then we take the derivative of the inside. Well, what's the derivative of negative 3x? It's negative 3, right? So this negative and this negative will cancel out, so we'll be left with positives. This 3 and this 3 will cancel out, so we're just left with 1 over x, which is oddly enough because the derivative of this and the derivative of this gives us the same answer. Alright, so that's something interesting. So for one of the last ones is when we take the derivative of no longer functions that look like e to the x, right? Because e to the x is very simple. The derivative of this is just e to the x. But what if you have the derivative of something that's not e, right? If it's not e, because e is a special number. So if it's not e, some random number like d of the x, so let's say 4 to the power of x, and we want to find the derivative of this, it's not just going to be 4x, 4 to the power of x. It's going to be what you would think, yeah, 4 to the power of x times the natural log of the base of this exponent. So the base is 4, so natural log of 4 times, now what you have to do is take the derivative of this, of the exponent part. So what's the derivative of x? Well, it's 1. So let's do another one. So I know that was a little bit weird. So let's say, no, this is too hard. Let's try, okay, let's do this. 2 to the power of 2x, and we want to take the derivative. Well, every time you see an exponential problem, you'll know the first step is to write it itself, because the derivative of anything exponential is going to be itself multiplied by some other weird things. So now times, what's the base? Well, 2, so natural log of 2 times the derivative